Hello there, I'm Victor Florentiev, and today I'm showing you my group's chemical processes script. Now, when chemical engineering a process, the engineer has the difficult job of keeping track of many conversions. And when trying to test different changes of variables, crunching these numbers becomes a cumbersome process in itself. This script helps make an engineer's job much easier in changing variables up and maybe trying to optimize a process. So you got many variables to keep track of. It looks pretty simple on the outside. You got fresh feed, reactor, cooler, condenser, condensate, purge, recycle. Maybe not too simple. But all of these, there are mole fractions that change with every little thing. And it all depends on what's in, how good the recycling is, how good it's condensing, all this stuff, purging. It all depends on it. And there's a lot of math behind it, and it's something that a computer can handle pretty well. Now my script, it accepts the mole fraction of inert gas. So this I right here, it tells you the fraction of moles of the I, the fractional conversion of the reactor, how good the reactor's at converting, and the fraction of the gas leaving, this purge right here. Ooh, how much is leaving versus how much is being recycled, right? Alright, now let's bring up the script. Let's start it. It asks you right off the bat, enter the mole fraction of inert gas. Let's say it's 0.3. Fractional conversion of the reactor. Let's say it's 0.2. Fraction of gas leaving the reactor, 0.6. This is and it spits out at you a lot of information, but it's all given to you in graphical ways as well as numerical ways. So you have figure 1 telling you the YP, which is the fraction of gas leaving, versus the NP, which is the moles of ammonia produced, which all of this is against NP. It's all about how much ammonia you're producing because you're trying to optimize this process. Figure 2 tells you the fractional conversion of the reactor versus how much ammonia is produced, and figure 3 is telling you the mole fraction of inert gas. Now it also tells you a recommendation based on the graphical observation, what you should do in order to optimize, like what you should be going toward. Should you be having more inert gas or less inert gas, as well as would you like to have a reactor with higher FSP or lower FSP? It tells you, I recommend you reduce the mole fraction of the inert gas fed into the reactor as well as the fraction of gas expelled, which makes sense because the more gas expelled, the less can be recycled, and the less inert gas, the more non-inert gas. And maximize the fractional conversion of the reactor for maximum yield, because the better it is at converting, the more you're gonna have, really. So, and then it tells you your maximum production of ammonia is 0.1 moles per 1 mole of flow in. So you're getting about a tenth. You have a mole of flow in, and you're only getting 0.1 moles. And it also tells you the theoretical maximum production of ammonia. It tells you how much is possible for this reactor to get the highest amount. And it is 0.5 moles, so you can see you're 5 times off with what you entered in. Let's say, I'm going to go with that, right? What is the total number of moles for flow into the reactor? So, because this is all on a 1 molar basis. You need it on a multimolar basis because it's not always 1 mole going in. Let's say you have 300 moles of flow into the reactor, which is shown right here, how much you're putting into the fresh feed right here. So let's go back, and let's say you have 300 moles, right? Enter 300. It tells you the cost to cool your reactor. It's $85 for 300 moles, right? So let's say that you want to take their advice and you want to reduce the amount of inert gas. You want to increase the fractional conversion, as they said, or as the code said, and you want to decrease the amount of purge. So let's do that. Let's, instead of 0.3, we'll have 0.1. Instead of 0.3 for the fractional conversion, we want it higher, so let's have 0.5. And a fraction of gas leaving, it was 0.6, so let's move it down to 0.2. You know, take their advice. Let's see if it actually gives us more. So yeah, it went up by a considerable amount. So taking their advice even a little bit, it wasn't like 100%, moved us up from 0.1 moles of production of ammonia to 0.38. So this just streamlines it for the user, really. And as you can see, we're pretty close to the theoretical max. Again, you ask you for the total number of moles, you know, and the cost to cool the reactor would actually be lower. It'd actually be lower. Another thing the script can do is you can ask it to enter other values, and it will tell you the cost to cool the reactor. So based on the other values. So would you like to enter other values? Yes. You know, let's have, you know, 0.2. Number of moles 500. Right. And it tells you the cost to be cooled. Would you like to enter the values? Nope. I'm done. Okay. So that's how the code works. Well, no, that's what the code does. Now let's see how it works. So what it does is it takes the numbers that the user entered, sends them into this process inputs function, which is right here, runs them through, does all the steps needed that the engineer would have been doing. But instead of, you know, an engineer being paid full time to just crunch these numbers at the, you know, behest of some, you know, person that's trying to figure out the optimal running conditions for the reactor, we have the computer program doing it for us. And it goes back to the main script. It takes all the inputs back. You know, it graphs these out per each point using a for loop, and puts them on figure 1, figure 2, figure 3, all with different colors to kind of visually guide the user. It gives them the recommendation. It calculates the theoretical maximum production of ammonia and the maximum production that under the user's variables, and it does the equations for the molar flow. So these are all just equations that, you know, chemical engineers use, hard-coded essentially into the script. Now that kind of brings us to a limitation of the script, is it's hard-coded, so you can't really use this on other reactions. You'd have to hard-code another way. You know, in the future maybe we could make a script that allows you to have more play, have a different type of reactor with different things flowing in, have maybe allow you to set reactors that have, you know, how many reactors are there? Is there only one? Where are the splits? This is all possible to be coded. So this is definitely a huge limitation. But for something like this, it can make, for just this reaction, it makes life easier. Absolutely. Well, thank you for watching, and I hope you have learned a little bit about chemical processes and the kinds of things that, you know, the kinds of things that you can do with computers and chemical processes, because it is the future. Thank you. Another thing that this script can do, and that we put in, is it kind of generates a little diary of this command window. You know, the command window is all right and all that, but let's say that you want to send this, you know, command window to somebody, you know, and the person has a Mac. You know, you can't just send them a Word document, or you couldn't at one point. Well, what this does is automatically at the end of the script, it outputs a text file, and this text file has everything. It has the entire thing. Just essentially a diary of all the things that he's entered and all the runs. You know, it tells you next run right here every time he has another run. So it allows you to send the data that you figured out to someone else. You know, so this could save time, because you could send this. You can make an intern do this and put these numbers in and figure it out, and then send it to the main engineer. And then, this can absolutely save time. So thank you.